Video 38 of the master course Quantum Chemistry of Molecular Electromagnetic Properties. The topic of this lecture is Induced Magnetic Fields and NMR Parameters. In the last lecture, we looked at the permanent molecular magnetic induction coming from the motion of the electrons, their orbital motion, and the spin of the electrons, and how these molecular magnetic induction then in the interaction with nuclear magnetic moments can lead to a change in the energy of the electrons. What we want to do in this lecture now is to expose our molecule again to an external magnetic field. So now we have two magnetic fields which we have to be careful to distinguish: the external magnetic field from a big magnet and the molecular magnetic field or magnetic induction coming from the spin or the motion of the electrons. Now, of course, if we, like when we discussed the molecular magnetic moments and the magnetizability, when we expose a molecule to an external magnetic field, this will change the current density, current distribution of the electrons. It will get polarized, and we will get, in that case, we talked about induced magnetic moments. So the same will of course also happen here. If we change the current distribution, then we will also change our molecular magnetic induction, which means we will also get from this induced current density, we will also get an induced molecular magnetic induction. So our molecular magnetic induction now in the presence of an external magnetic field will be the permanent molecular magnetic induction plus an induced molecular magnetic induction. And both, of course, are fields. And the induced molecular magnetic induction then depends on the external magnetic field. And it will, of course, also depend on internal magnetic fields, meaning it will also depend on the magnetic moments coming from the nuclei, because they, as we already had discussed, also change our current density. So like always, we will now expand this induced molecular magnetic induction in a power series, where here I only write up the linear terms. So I have a term, a contribution to this induced molecular magnetic induction coming from the external magnetic field, which is linear in the internal magnetic field, and the proportionality constants. Here I write up the same symbol as we already had when we discussed molecular magnetic moments and the induced molecular magnetic moments coming due to the interaction with the nuclear magnetic moments in the molecule, this absolute shielding tensor. And we will see that this actually is going to be related to each other. And we get also a term linear in the nuclear magnetic moments. Now let's look at this shielding term here. Since we are looking at a field, a magnetic induction, this is also a field, and I call it the magnetic shielding tensor field. It's a generalization of the magnetic shielding tensor, which we had in the chapter on the magnetic moments already, to an arbitrary point in space. So the product of this magnetic shielding tensor field and the external magnetic field is the induced molecular magnetic induction at a particular point in space due to the external magnetic field. And our nuclear magnetic shielding tensor of nucleus K of NMR spectroscopy is just the value of this magnetic shielding tensor field at the position of the nucleus. But of course, we can define this field, or we can calculate this field at any point in space, and in particular any point in space inside the molecule, but we only can measure it at the position of the nucleus, and there we call this the nuclear magnetic shielding tensor. Correspondingly, we have this K field here, which I call the reduced indirect nuclear spin-spin coupling tensor field. It's also a field because it is defined for every point in space. And the product of this field with the nuclear magnetic moment of a nucleus L is then the induced molecular magnetic induction at an arbitrary point in space due to the interaction with this magnetic moment of nucleus L. And again, this is the generalization. This reduced indirect nuclear spin-spin coupling tensor field is the generalization of the coupling tensor, which means the reduced indirect nuclear spin-spin coupling tensor K, KL alpha beta, is just the value of this field at the position of nucleus K. And this reduced indirect nuclear spin-spin coupling tensor is related, actually it's just proportional, to the spin-spin coupling constants which we know from NMR spectroscopy, which normally is called J. The difference between the two of them is essentially just the nuclear G factors and something for the units. Which means, I mean, the J coupling constants from NMR spectroscopy, which directly can read off from the NMR spectrum as the distance between splitted lines, depends on the G factors of the two nuclei involved. And here in the reduced one has divided by those G factors, so the reduced coupling constants does not depend on the G factors of involved nuclei, which means the reduced nuclear coupling constants is the same for example, a proton and a deuterium, whereas of course the J coupling constant is quite different because proton and deuterium have quite different G factors. So the difference in reduced coupling constants tensors between, for example, different nuclei is only a question of the changes in the electronic structure, and not because it has a different nuclear G factor. So the local magnetic induction, which a nucleus K experience, which is the value of our magnetic fields at the position of this nucleus K. So it's of course the value of the external homogeneous magnetic field plus the value of the induced molecular magnetic induction. In principle, it also would be, of course, the value of the permanent molecular magnetic induction. But in the following, I only will discuss closed shell molecules, and for closed shell molecules, the permanent molecular magnetic induction is zero, like the permanent magnetic moment is zero. So therefore, what a nucleus K in the closed shell molecule experience is the external magnetic field of the store magnet, the big magnet of an NMR spectrometer, plus the induced molecular magnetic induction induced by this external field. And inserting the expression from before, now that we look at a particular point, the position of nucleus K, we have here now a term which has the shielding constant of nucleus K times the external field and the reduced coupling constant of nucleus K with all the other nuclei L. Combining the first two terms in one, we arrive at the well-known expression for the local field at the nucleus K in NMR spectroscopy, which here now written in tensor components is the Kronecker delta minus the shielding tensor component of nucleus K. The shielding constants, which one normally obtains from gas or liquid phase NMR spectra, is then just the trace of the diagonal elements of this shielding tensor. So it's the sum of the XX, YY plus ZZ, or in general of the diagonal elements divided by 3. However, what you actually get from an NMR spectrum is not this magnetic shielding constant, but it's what is called the chemical shift. And let's discuss that now, how this comes about. Now, the resonance frequency of a nucleus K, UK, that's the frequency of the allowed transition between two nuclear spin states of a nucleus. So we need to know what is the energy, and that is, of course, the energy difference between the two states divided by Planck's constant. So we need to know what the energies of the nuclear spin states are. Well, that's of course the product of the magnetic moment of the nucleus with the magnetic field at the position of the nucleus. And the standard definition is that the orientation of the field defines the Z component. So we have the Z component of the magnetic moment of the nucleus and this Z, which is the only component of this local field at the position of the nucleus. Now, if we replace the Z component of the magnetic moment with the corresponding Z component of the spin of the nucleus, and remember that, of course, spin is quantized, in particular the Z component of a spin is quantized, here with the quantum number mi of the nuclei. And then we also have to remember or accept that the allowed transitions for nuclear spin states are only the ones where the quantum number of the Z component of the nuclear spin changes by 1. And therefore we can have energies. The energy difference is always which involves a change in mi by 1, as written here. Inserting all the expressions, then we end up that the resonance frequency for allowed transition is here some natural constants, then 1 minus the shielding constant of that nucleus times the Z component of the external magnetic field. And that's for a molecule in the gas or liquid phase, where the molecules fast enough rotate so that we just get the isotropic interaction with the shielding constant and not the tensor elements. Now, from this expression, one might believe that if one measures the resonance frequency and, of course, knows the external magnetic field of the spectrometer, then one easily could get the absolute shielding constant or the shielding constant. However, the problem is that we don't really know actually the external magnetic field, because if we could have a spectrometer where we could have a single molecule in vacuum in the magnet, then we could do that, but we can't do that. We measure NMR spectrometer normally having a molecule in solution in some solvent, and the same kind of shielding effects of extra induced magnetic inductions, which we have discussed here in terms of within the molecule we're studying, of course, happens with all the solvent molecules, and it happens with the material of the probe, the class of the material, which means there are extra components, extra contribution to that local field, which we don't know and have no chance to measure. So we actually don't know what the magnetic field outside of the molecule is, which this one would be. That's the one outside of the molecule. We know what the magnetic field of the magnet is, but we don't know what is the magnetic field in our probe, which is something in solution, or molecule in solution, just outside of the molecule. So what one does is then one defines this chemical shift, which is the relative resonance frequency. So one takes the resonance frequency of the nucleus which we're interested and subtracts the resonance frequency measured in the same experience for some reference molecule and divides by the one for the reference molecule and then has to multiply it with 1,000,000. And that's the chemical shift. Now, of course, we can insert our expression for the resonance frequencies now, and then the unknown external magnetic field, external outside of the molecule, but not the field of the spectrometer, drops out of the equation. And we have here the well-known relation between the chemical shift, which is what we get out of the NMR spectrum, and our molecular property, which is the shielding constant of our molecule which we're interested in. Which means if one wants to calculate the chemical shifts, one also not only has to calculate the shielding constants of the molecule we're interested in, but also of the reference molecule. And then one can calculate the chemical shift. And to make the distinction between the chemical shift delta and our shielding constants more clear, one calls the nuclear magnetic shielding constant also often as the absolute nuclear magnetic shielding constant. And the negative chemical shift, here negative chemical shift, implies that the nucleus is more shielded in the molecule we're studying than in the reference molecule. And vice versa. A positive chemical shift is then corresponds to a nucleus who is less shielded in our molecule of interest than in the reference molecule. Now let's talk about the spin-spin coupling constants. The spin-spin coupling constants, I mean, we have magnetic resonance spectroscopy, so the interpretation of the spectra is done in terms of an effective spin Hamiltonian, which now has two contributions. It has the contribution which includes the external magnetic field and the nuclear spins. So it's a coupling between the external magnetic field and the nuclear spins, which involves the local magnetic field. So here we have our shielding constant again. But then we also have a contribution to that, because if you look, if IK is the K nuclear is the one we're interested, then there's a coupling with all the other nuclei which have spin, which of course also leads to a change in the energy of the system, this coupling. The DJ is the one which we already had, which is related to the reduced indirect nuclear spin-spin coupling constant or tensor K, whereas D is the so-called direct through spin dipolar nuclear spin-spin coupling tensor. That's the interaction between the two nuclear spins without any involvement of the electrons. So D is the direct one, whereas J, that's the electron-mediated coupling. D can be measured in solid state NMR spectra, but not in gas phase or solution NMR spectra, meaning it cannot be measured when the molecules have the possibility to rotate freely. So we're not going to look at this term. All the terms in the nuclear spin effective Hamiltonian, which depend on the involvement or which include involvement of the electrons, like here the shielding constant and here the indirect nuclear spin-spin coupling constant tensor, the contribution to the energy of the system from these terms we also can analyze by looking at the change of the energy of the electrons due to this interaction with the nucleus. So it's vice versa. So we can look at the change in the electronic energy due to the interaction between the nuclear magnetic moments and our molecular magnetic induction, which is of course the induced molecular magnetic induction, or has also contribution from the induced molecular magnetic induction. So I've written it up here in terms of the energy of the electrons. So we have the term the permanent molecular magnetic induction with the nuclear magnetic moments. And here I have all the rest is now the induced molecular magnetic induction interacting with the magnetic moments. And in the first term, we have the induced molecular magnetic induction induced to the external magnetic field, that now interacting with the magnetic moments of the nuclei. And in the second term here, we have the induced molecular magnetic induction due to nuclei L, and those interacting with the magnetic moments of nuclei K. And if I know or introduce the relation between the reduced coupling constants and the normal J coupling constants, I can also write it in this way. Now in my final slide, I have now written up or collected in a table the definitions of all the molecular response properties which we have discussed in this chapter so far, starting with the magnetizability. Sort of that's a repetition, and then we have the nuclear magnetic shielding field, nuclear magnetic shielding constant of nucleus K, the reduced indirect nuclear spin-spin coupling field, and the value of this at the position of nucleus K. So it's the indirect nuclear spin-spin coupling constant between nuclei K and L. And we can define them as response properties, meaning as first derivatives of some other properties, where we can define them either as derivatives of the molecular magnetic moments, where the polar magnetizability is the first derivative with respect to a magnetic field. I mean, it's the perturbed molecular magnetic moments, so the molecular magnetic moments in the presence of an external field and in the presence of nuclei with magnetic moments, where the magnetizability is the derivative with respect to a component of the external magnetic field, and the shielding constant of nucleus K is the derivative with respect to a component of the magnetic moments of this nucleus K. We can also express some of these properties as derivatives of our molecular magnetic induction, here in the presence of the external field or of nuclear magnetic moments, where the shielding constant field is a derivative with respect to the external magnetic um, induction, and our coupling constant indirect reduced coupling constant field is the derivative with respect to a nuclear magnetic moment. And if we then look at those fields at a particular position, not the general position in space, but the position of nucleus K, we get then the shielding constant or the reduced indirect nuclear spin-spin coupling constant. But we can also, from the last expression on the slide before, we can express them also as derivatives of the energy, where, as we had in the last chapter or 2 chapters before, the magnetizability is the second derivative with 2 components of the magnetic moments. The shielding constant is a mixed derivative, as one derivative with respect to a component of the external magnetic field, and one is with respect to a component of the a nuclear magnetic moment. And finally, the reduced coupling constant is also in reality a mixed derivative, but it's 2 derivatives. The 2 derivatives are with respect to 2 components of 2 different nuclear magnetic moments. And in the following lecture, we will now use these definition as derivatives of first derivatives of moments and fields, or second derivatives of the energy, to derive quantum mechanical expression for these properties.